Hello, YouTube. This is the DiffyQ day, more so than the other days, which were honestly pretty much DiffyQ days as well. Today we're going to be talking about how to handle things where you've got multiple things in an equation that are related to each other, and then go from there. So, ideally, end of the day, you should be able to model the motion of an object with forces that are changing over time. So this is different from everything we've done so far because the forces are actually going to be varying as you go. To do that, the big things are you integrate it with respect to time and use DiffyQ to model it, dependent on like if it's something. If the forces are dependent on something's speed, that would be like with drag, or if the forces are dependent on something's location. And those are sort of the first of the 3 or 4 different like sets of things you'll have to do. We've already done a little bit of this with drag, where pretty much we just said, look, if there's only 2 variables, time and something else, what you can do is you can take those 2 variables and you can shuffle them around and you can integrate it and you'll be fine and it'll work. You have to be a little bit careful of that if you've got the second derivative. If there's the second derivative, yeah, I mean that's pretty much it. You will have to be more careful with that. So pretty much forces don't always remain constant. If there's a good way to predict or model the forces, use it, but like most of the time it's going to be awful. A lot of the times for variable forces, what you're going to do is just use energy or use momentum, because those things are tools designed to get around using horrifically complicated things like we're going to have to talk about today. If you can't do that, specifically, if you can make an equation that tells you about the force in terms of something else, you are probably supposed to use forces. There'll be exceptions for that, especially if you only care about velocities. You're probably supposed to use energy. But generally speaking, that's a good indicator that forces will work, and so you can go that way. If it's forces in terms of time, that's actually pretty easy comparatively, because you can just treat it like the kinematics equations instead of having like acceleration is equal to a constant. If you think back a ways, there were all those equations that were like your acceleration is a function of some set of variables and time is the only variable in there, and you could just take the integrals to get the kinematics equations. It's that you can do the same thing. So like if we've got something like this, where a fan is applying a 40 Newton minus 4 Newtons per second times time worth of force to a block, and we have the mass of the block. It starts at rest, and then the batteries are dying, and that's why it's providing less force over time. That was not particularly well written. So basically the fan stops once the batteries are dead. So it'll start to speed up because the fan is pushing it more than friction does, and then eventually it'll start to slow down as the fan dies. And the question is, how far does the block travel before it stops? So, getting all our info for this one down. Oh, fixing the camera so that we can get all our info for this one down. We've got we've got a fan. We've got an amount of force on it that's going to be equal to 40 newtons minus 4 newtons per second times our time. And that'll equal the force from our fan. Backwards, we'll have the force of kinetic friction. And we'll have a normal force going up and mg going down. And thankfully there's no angles or anything to make it just that little bit more difficult. All right, cool. So if we're trying to set up our Newton's second law equations, It'll just be net force equals ma. We'll do it for the x direction and the y direction as we've been doing so far. In the y direction, we'll have that our normal force minus mg is equal to 0, which means that our normal force is equal to mg, just subtracting that off from both sides. In our x direction, we'll have that our fan, which is providing a positive force, minus our force of friction will equal our mass times our acceleration. And we're asked about how far this thing goes before it stops. So what we really need is a set of kinematic equations, or a set of equations that sort of dictate where this thing's going to be at any given time, and how fast it's going to be going at any given time. So what we can do for that is get our equation set up. Now, thankfully, our force of friction is going to be a constant. Our force from our fan is going to be variable. Doing that out, we've got that our force of friction will need to be equal to mu times Fn, which means that our force of friction is going to be mu mg. So I can take that and plug that in here. We'll get the force from our fan, which, plugging that in, is 40 minus 4 times t minus mu mg is equal to ma. Divide each side by the mass, divide each side by the mass, and we've got an equation for acceleration. The problem is we don't want an equation for acceleration, we want an equation for distance. So we need to integrate. And not too bad, because all we have to do is integrate with respect to time. And when we do that, what we'll wind up with is 40 times time minus 2 times squared minus mu mg times time will equal our velocity as a function of time. This is nice because we're going to need to solve for time when velocity is equal to 0, because that's going to be how far it travels before it stops. Now, I need to be a little bit careful about that one. Because I need to just plug that into this term, because if you take a look at this real quick, the batteries are dying and eventually they'll die. Once they die, this will just be 0. It can't go negative. So this actually needs to be a piecewise defined function, and we need to be a little bit careful about that. So the batteries die in some amount of time. To figure out how long, we can take that force from the fan and set it equal to 0. Solving this out, minus 40, negative 4 times t is equal to negative 40, divide by negative 4. We'll get that it takes 10 seconds for the fan 10 seconds for the fan's batteries to die. We can take those 10 seconds for the fan's batteries to die and plug them in over here. And so this is going to be useful because if the time we get here when we set our velocity equal to 0, the time when it stops, is bigger than 10, then we know we've gone too far. So we're trying to solve for time. We can factor out a t because every term's got a t in it. So we'll have 40 minus 2t minus mu mg, which is 0.3 times 5 times 10. And that'll get us our time until it stops. We'll either have time equals 0, or if we come over here and do this, we'll have 40 minus 0.3 times 50, which 0.3 times, well, it's just 3 times 5, so that's 15. So that'll be 40 minus 15, which is 25 minus 2 times t equals 0. That gives us that 25, if we add 2t to both sides, plus 2t is equal to 2 times t. Divide by 2, divide by 2. And if the fan could go backwards, which it can't, it would take 12.5 seconds. So actually we have to be careful about this one and set up a piecewise defined function. What we'll get here is, and this is going to take a little longer than I had hoped, but oh well. What we'll get here is that for the first 10 seconds, this equation holds. After 10 seconds, our acceleration is just mu mg, because there's no fan, it's just gravity, which is going to be 15 newtons. Oh. All of that needed to be divided by 5, so I'm not going to need to do piecewise. So this is over m. That won't matter. So this is all over m. Because we're setting it equal to 0, that won't matter. We will still need to do piecewise. Jeez Louise. Okay. So our acceleration is equal to that over m, which means that our acceleration is 3 meters per second squared after 10 seconds. So we'll need to figure out what our velocity at 10 seconds is to be able to figure out what our kinematic stuff for after 10 seconds is going to look like. Before we do that, I do need to figure out how far it goes before that time. And then we can take the distance it travels while the fan is on, add that to the distance it travels while the fan is off, and we'll actually get our stuff. So, to get our distance it travels while the fan is on, we need to take our velocity equation and integrate with respect to time. When we do that, what we'll get is 20 t squared minus 2/3 t to the third minus mu mg over 2 times t. Not going to forget that that's all over the mass this time, and that'll be equal to our position. So if I take this and I plug in 10, that'll give me how far it's gone before the batteries die. Plugging in 10, we'll get 20 times 100 minus 2/3 times 1,000 minus 15 over 2 times, oops, that should be squared, times 100, and that'll equal our position, divided by our mass, which was 5. We'll have 2,000 minus, oh gosh, 15 times, I have a calculator right here. 2,000 minus 2/3 times 1,000 minus 15 times 50. All of that's getting divided by 5. All right, so it goes 116.7, and I'm just going to call that 117 meters in that 10 seconds. That's not our answer, but we're getting pretty close. Our velocity at 10 seconds, we can take that velocity equation and divide that by the mass, which will get us 4 times 10 minus 2 times 10 squared minus 0.3 times 5 times 10 times our time of 10 divided by our mass of 5. So 400 minus 200 minus 15 times 10, 150 divided by 5 is 10 meters per second. So it's going 10 meters per second when the battery dies. So now what I can do is find my displacement for the second section, using that my initial velocity for the second section is 10 meters per second. My final velocity for the second section is 0. My acceleration for the second section is negative 3 meters per second squared. This needs to be negative because it's going backwards. And then it's just a kinematics equation. I have Vx squared equals Vx naught squared plus 2a delta x. Picking this one because it's got the same variables as over here. This is equal to 0 because our final velocity is 0. Subtract 2a delta x from both sides. 2a delta x is equal to Vx naught squared. Divide each side by 2a. Divide each side by 2a. Negative, negative, and what we'll get is that our displacement is equal to negative Vx naught squared divided by 2a, which is equal to 100 divided by 2 times 3, and 100 divided by 6 is 16.7. So 17. So all we have to do is add those together, and there's our final answer. Woo! That's the easy thing we're doing today. So briefly going over the process again, pretty much we had an equation where we knew what the force was in terms of time. That let us integrate once to get a velocity equation and a second time to get a position equation. We did have to be a little bit careful because we had a situation that had to be piecewise defined because the force couldn't go negative, but the equation would make the force go negative after a certain amount of time. So that equation was only valid up to 10 seconds, which is what made this one so weird. Normally you could just solve for the times, plug them in, and you'd be done. Okay. So sort of summarizing that up, you use Newton's second law, that'll get you an equation with respect to time. You can only do this when you have Newton's second law in terms of time. Once you have that, you can integrate it twice. This will get you your equations that will allow you to actually solve for whatever it is that you're looking for the actual problem. So if you have one constant force for the first part and then you have a second constant force for the second part, that would actually wind up being a second thing that would get you piecewise defined equations, but those tend to be a little easier. Or if you have variable forces for one part and then constant forces after a certain time, like we did for the last one, that'll also make a set of piecewise defined functions that you have to actually be careful with the two of them to figure out where it's going to be, and then use that to figure out where it's going to be, how fast it's going to be, all that good stuff. This is a situation that's a little weirder. And the reason that this one is weird is because position is changing with respect to time. Acceleration is also changing with respect to time. So you cannot just integrate the way that we have been previously. So this is a differential equation. There's two really key features here. The first of which is that this term, k is just some constant. This term is a second derivative. This term is just the thing. There are some ways that this can play out when you get to rotational motion and stuff, where this same equation will come up again, without it just being position and acceleration. But it should always be something that's similar to that, where it's two things that vary with respect to each other with a second derivative for this specific Diffie-Q problem that we're going to do. So you need to train yourself to recognize so far 3 different situations for diffie q. We're eventually going to add a 4th. So the 3 so far are, if you've got something where it's the first derivative with respect to time, so some constant times your velocity is equal to your position is equal to the thing. If you've got your second derivative equals some stuff times time plus some constants times time squared, something as a function of time. That's your second setup. This one's less of diffie q, it's just straight up calculus. So really there's only 3 diffie q equations you have to deal with. This one, and then this one we're about to talk about, and then a third one. The last part of this that's really important is that this is positive. If this is negative, there are completely different rules, because the derivatives will work very differently if it's negative versus if it's positive. If it's positive, what we're going to have to do is be a little careful here, because I can't just say that this thing is equal to the second derivative of x with respect to time twice is equal to kx. I can't just integrate that twice. It just doesn't really work. Specifically because of it's one of the few times where we do have to actually be careful so that math people don't get super, super mad. What we can do, and this is how we would solve it if we were doing it this way, is we'd be like, okay, well, this thing is equal to the derivative of this with respect to time. I can split these two up. I can get all the x's on one side. I can integrate it. That'll get me ln, and I'll be good to go. It'll be fine. That doesn't really work for us with the second derivative. What we can do instead, though, is we can think of acceleration as the derivative with velocity with respect to time. And this is sort of the type of thing where it's like, if you didn't know that you were supposed to do this, there's no way you would be expected to do it. But because we can learn that we're supposed to do it, you're going to be expected to know how to do it. This next step is going to seem really arbitrary, and it's so that things will work out. Using the chain rule, the derivative of velocity with respect to the time is the same thing as the derivative of velocity with respect to position times the derivative of position with respect to time. Basically what we're doing is we're taking a fraction, like for me, the way to remember this, we're taking a fraction and we're multiplying, like we've got a over b, we're multiplying it by c over c. And the reason we know we're supposed to be multiplying it by c over c is that it's equal to some stuff times c, and that'll make our life easier. So there's sort of an a term, a b term, and a c term. You take that a term, which is your derivative, and that b term, which is the second half of your derivative. You multiply it by the c term over the c term, so the thing on the other side over the thing on the other side. When you do this, the reason why this is particularly useful, that's velocity. And once we've done this, we'll get the derivative of velocity times the velocity divided by the derivative of x equals kx. And the reason that this is particularly good is we can multiply each side by dx. And what we'll wind up with is that v dv is equal to kx dx. We can integrate both sides, and we've got an equation that we can work with. 1/2 velocity squared is equal to k over 2 x squared. And that's a relationship between those two things and how they'll function. So trying to verbally write that. You're only doing this thing when you have three variables or a second derivative like acceleration without a negative sign in front of it. So this is with positive things. If it's a second derivative, or it, like this would also work if it had been written as dv dt. You want to turn it into the three variables using like the dv dt type thing. It should be a situation where it's like that. I'm actually going to go to this. It should be a situation like it's that a times b, a over b equals some constant times c. So that what you can do is from there, you can take that a over c, you can multiply it by c over c, or more accurately, the derivative of c over c. And when you do that, you'll get a situation like this. Specifically, you want to do it because the way these problems will be set up for you to have them on the AP exam, or more accurately, this only works when C is equal to, or the derivative of C with respect to B is equal to A. Because once you've done this, you can turn this part of it into just A. And then you can actually wind up solving it. And that's what the rest of the text is trying to get at. Two of them should be related via a derivative, ideally with respect to the third thing. In fact, it pretty much has to be with respect to the third thing in order for it to work. Velocity is the derivative of position with respect to time. That's the one that we had from the example. You represent the derivative of the first thing with respect to the third as the first with respect to the second, and the second with respect to the third. So it's just that fraction thing where you're multiplying by the thing over the thing, and then you're swapping it around. And like technically you're not supposed to do that or whatever, but whatever. That second one with respect to the third should let you get rid of the third variable, because that'll be the first variable again, and that'll get rid of the existence of the third variable. You'll only have the first variable and the second variable, in this case A and C, velocity and time. Or sorry, velocity and position. And you should only have to do that in that one specific case where you see that one specific equation form, or something else that looks similar to it. I want to go into a more concrete example. I'm actually going to stop the video here and upload the more concrete example as a part B, because I'm a little hesitant about what will happen if I do it wrong. So goodbye, YouTube. See you in part B.